In this week, we will focus on the concepts of the subsequence and of its limits. The idea behind the subsequence is given by one very simple example. Think about the sequence xn, where the terms are given by -1 raised to the nth power. These terms alternate between -1 and +1. So while we know that the sequence does not converge, in a moral sense, we kind of would like to be able to say something like, this sequence converges to both -1 and +1. The concept of convergence that we discussed 2 weeks ago for sequences does not allow that. Remember, a sequence can have no more than one limit. In this week, by thinking in terms of subsequences, we can think about how to properly describe the behaviors where a sequence ought to have more than one limit. The behavior of the limit sets can be pretty complicated. We will prove a few simple theorems about them by the end of this week. In this lecture, we will begin by defining the notion of a subsequence. This corresponds to what is discussed on pages 66 and 67 of your textbook. Let's first give the formal definition. Given a sequence x sub n, a subsequence, which we often write as x sub n sub k, is a sequence formed by selecting a number of terms from the original sequence. The selection process is described by n sub k, which is itself a sequence. This sequence tells us which term of the original sequence, in terms of its position n, is selected as the kth term of our sequence. So n sub k is itself a sequence, meaning that k runs from 1, 2, 3 all the way out to infinity. In particular, a subsequence must itself be infinite. It is not a finite selection of the terms of the original sequence. Additionally, since we are selecting terms from the original sequence by selecting their indices, the values of n sub k are natural numbers. And finally, we impose a rule. The selection cannot be done willy-nilly. The selected sequence must be strictly increasing. So for example, if the first term you chose for your subsequence is the third term x3 of the original sequence, then you've given up your rights to x1 and x2 and cannot select them going forward. The second term of your subsequence, you can select any term of the original sequence from the fourth term onward, since the first term you've selected to be x3. In this way, n1, the position of the first subsequence term within the original sequence, is less than n2, the position of the second subsequence term within the original sequence, and so on. It is worth pointing out that in the notation x sub n sub k, the subsequence is indexed by the letter k. N sub k tells you how to translate from the numbering within the subsequence to the corresponding numbering within the original sequence. It is in situations like this that it is convenient to indicate outside of the parentheses the letter with respect to which you are doing the indexing. We can think of the definition in a slightly different way. Under the hood, these two ways mean the same thing. I'm just describing different ways of interpreting the definition. Remember that we talked about how a sequence is really representing a function whose domain is the natural numbers and whose codomain or range is the real numbers? The increasing sequence n sub k that corresponds to the selection of terms of the original sequence is then itself a function from the natural numbers to the natural numbers. So thinking in terms of functions, the function that corresponds to the subsequence x sub n sub k is nothing more than the composition of the function corresponding to the original sequence x sub n against the selection function for n sub k. The two definitions may give rise to somewhat different visualizations. You should certainly choose the one that best helps you imagine the scenario. Let's start with a few simple examples. In the first example, the original sequence x sub n is given by -1 raised to the power n. If we choose the selection function n sub k being equal to 2k, then the corresponding subsequence x sub n sub k is equal to 1 for every k. This is because we can just plug in the value 2k for n sub k into the value of n in the formula for x sub n. This gives us that minus 1 raised to the power n sub k is nothing more than minus 1 raised to the power 2k, which is minus 1 raised to an even power, which gives us 1. In the second example, the original sequence x sub n is given by the fraction n over n plus 1. The selection function is given by n sub k equals 10 to the power k. This means that the first term of our subsequence is the 10th term of the original sequence. The second term of our subsequence is the 100th term of the original. And the third term of our subsequence is the 1000th term of the original, and so on. Plugging this in, we see that the subsequence x sub n sub k, which we remember is indexed by k, has a formula in terms of k given by 10 to the power k divided by 10 to the k plus 1. The first few terms are 10 over 11, 100 over 101, 1000 over 1001, and so on. To reinforce our understanding of what counts and what doesn't count as a subsequence, let's look at a few non-examples. In the first case, let x sub n equal n. So the original sequence is 1, 2, 3, 4, 5, 6, and so on. The list 1, 2, 4, 3, 5, 6, formed by transposing the third and fourth terms, is not a subsequence. This is because in forming the subsequence, the selection of the index cannot allow a later index to be selected first, before a prior index. In the second case, let x sub n equal 1 over n. The list 1, 1 half, 1 half, 1 quarter, 1 quarter, 1 quarter, and so on is not a subsequence because it repeated 1 half twice and 1 quarter 3 times. Both of those terms appear only once each in the original sequence. To form such a list, the n sub k must be in order 1, 2, 2, 4, 4, 4, which is not strictly increasing, and thus the list does not correspond to a subsequence. In the third case, the original sequence looks like 1, 2, 2, 3, 3, 3, 4, 4, 4, 4, and so on. For the list 1, 2, 3, 4, and so on, this can be achieved as a subsequence. In fact, there are many ways to do this. N sub 2, for example, can either be 2 or 3. And n sub 4 can be 7, 8, 9, or 10, since the term 4 appears as the 7th through 10th term of the original sequence. On the other hand, if we try to write down the list 1, 1, 2, 2, 2, and so on, this cannot be a subsequence since 1 only appears in the original sequence 1 and 2 only appears twice. To get those two numbers to appear twice and thrice respectively, there must be repeats in the n sub k's. So, to summarize, in order to extract a subsequence from an original sequence, we are allowed to skip over some number of terms, as long as we're still left with infinitely many. But we are not allowed to repeat previously used terms, nor are we allowed to reverse the order of the terms. Next, we describe some basic properties of subsequences. First, every sequence is a subsequence of itself. This is similar to how every set is a subset of itself. To realize this subsequence, we can take the selection function n sub k to be equal to k. Thus, the first term of the subsequence will be the first term of the original, the kth term of the subsequence will be the kth term of the original, and so on. Second, if we are given an infinite subset of indices, so this means an infinite subset of natural numbers, we can form a subsequence corresponding to these indices. By listing as our n sub k the kth smallest element of the infinite subset. As a consequence of this, if the original sequence is such that the same value z is taken infinitely often, then there must exist a constant subsequence where each and every term of the subsequence is equal to z. To illustrate the final consequence, consider the sequence cosine of 2n pi over 3. The terms of this sequence works out to be minus 1 half, minus 1 half, 1, minus 1 half, minus 1 half, 1, and so on. As we can see, this sequence only takes two possible values, minus 1 half and 1. Each, however, it takes infinitely often. So there exists a subsequence that only yields the value 1 as its output. As an example of a selection function that does this, we can take the indices n sub k to be in order 3, 6, 9, and so on. There also exists a subsequence that only yields the value minus 1 half as its output. A simple selection function that accomplishes this has the terms of n sub k starting with 1, 2, 5, 8, 10, and 13. Before we go, a quick recap. A subsequence is formed from a sequence by selecting from it a certain infinite list of terms. Alternatively, we can think of a subsequence as being formed from a sequence by dropping from it a certain list of terms, taking care that infinitely many terms remain. In particular, the terms of the subsequence must appear in the same order as they appeared in the original sequence. Okay, that's it for the introduction to subsequences. See you next time.